Well, hello and welcome to lesson 22-2. We are about to embark on the trigonometric ratios. The trigonometric ratios, by far one of the most important maths we'll see in geometry, known as the trigonometric ratios. Before we dive into lesson 20-2 or 22-2, let's just take a minute and review kind of what we've seen up until this point. So here we have two similar right triangles. And just recall when we use this word similar at all, we use the word similar at all, we mean corresponding angles are congruent and corresponding sides are proportional, which means their ratios are equal. So it stands to reason that we have learned what similar triangles are up until this point. We studied the two properties of similar triangles, corresponding angles congruent and corresponding sides proportional. And now we're seeing this term known as trigonometric ratios because of what we explored previously about what it means for corresponding sides to be proportional. It means their ratios are equal. So imagine we have two right triangles here. Again, they are similar right triangles. We'll go ahead and label a couple key points, a couple key vertices. Remember, vertex is a point where two lines meet. Just get a couple points here, just so we know what we're talking about. So let's go ahead and make the claim that triangle ABC is in fact similar to triangle DEF. So we have these two similar triangles. Now, there's actually no information to suggest that they're similar. Just because they're two right triangles doesn't mean they have to be similar. But let's kind of explore that a little bit further. Again, we do know at least that one pair of angles is congruent because they both have a 90-degree angle. And let's go and establish that the measure of angle B down here is 30 degrees. And so the measure of angle E is 30 degrees. So these two triangles are now, without a shadow of a doubt, similar right triangles because we now know at least one measure other than that 90-degree angle. And recall that we can actually prove two triangles are similar just using two pairs of angles. In this case, the 30-degree angle and the right angle. That is known as angle-angle similarity. So we've just explored what does it really mean for corresponding angles to be congruent. And before we jump away from that, let's go and establish what the measure of angle A and what the measure of angle D has to be. So this is a pretty important idea as we move into 22-2. If this is a right triangle, if these two triangles are both right triangles, then in this triangle, C is already 90 degrees of the total 180 that the three angles of a triangle have to add to equal. It's called the triangle sum theorem. All three angles in a triangle have to sum to equal 180 degrees. So in a right triangle, if 90 degrees is already taken up by the right angle, then these two angles combined have to total to equal 90 degrees as well. If you recall, two angles whose sum is 90 degrees, they are referred to as complementary angles. Complementary angles, two angles whose sum equals 90 degrees. So how does that help us? Well, if we know angle B is 30 degrees, what can I add to 30 degrees to give me 90 degrees? So we know that 30 degrees plus 60 degrees is 90. So understanding what it means to be complementary, we can actually find that third angle rather quickly. Now, there are other ways to do it. Of course, we could have taken the 90-degree angle, added it to 30, got 120, subtract 120 from 180. But again, we're going to explore in 22-2 what's so unique about these other two acute angles and them being complementary. Now, something we explored in lesson 22-1 is a unique relationship in reference to the angles and their sides. So let me kind of clear this up just a little bit. So for example, we're going to say that B is our indicated angle. B is our indicated angle. In reference to B, we're going to say that this side, more importantly, this leg is now known as the opposite leg to B. So the opposite leg to B is side AC. And the adjacent leg to B, notice I use the term adjacent leg, because if I use the term adjacent side, we could be referring to the hypotenuse, but the adjacent leg is BC. So the adjacent leg to angle B is side BC. And of course, the hypotenuse of this right triangle is AB, which has nothing to do if we're looking at angle B or angle A, which either angle is the indicated angle. So the hypotenuse is line segment AB. Now, the reason we're defining this is because when we then look at angle A as the indicated angle, things change a little bit. So now when we look at angle A as the indicated angle, the opposite leg to vertex A, the opposite leg is actually line segment BC, which was the adjacent leg to angle B. So the opposite leg to angle A is side BC, which means that the adjacent leg to angle A is line segment AC. Notice these two legs have swapped their roles depending on which angle we're looking at. But regardless, the hypotenuse is still line segment AB. Remember the definition of hypotenuse, not just the longest side of a right triangle, but it's always opposite of the right angle. Regardless of which angle we're looking at, vertex C is our right angle, so line segment AB is always the hypotenuse in this triangle, regardless of what angle we look at. Now let's do something very similar to this other triangle over here, our other similar right triangle, and we'll start with angle E. I think that makes sense considering we've already established that angle E is congruent to angle B. So in reference to angle E, the side opposite, or the leg opposite more appropriately, the leg opposite to angle E is side DF. So the opposite leg is side DF. Therefore, the adjacent leg to angle E is side EF. The adjacent leg is side EF. And last, the hypotenuse of this right triangle, again, no matter if angle E is our indicated angle or not, the hypotenuse is side DE because it is opposite of the right angle. Now let's look at the indicated angle as angle D. And we'll kind of bring all this information to a conclusion here. So in reference to angle D, the opposite leg to angle D is actually side EF. Again, just like on the previous statements, we said that the opposite leg and the adjacent leg actually switch depending on which angle you're looking at. And likewise, in this right triangle, in reference to angle D, the opposite leg is side EF, which was actually the adjacent leg to angle E. Therefore, the adjacent leg to angle D, is side DF, which again was the opposite leg to angle E. And last but not least, the hypotenuse, just like it was previously, the side DE, the hypotenuse is side DE. Again, it has no bearings on whether or not which angle we're looking at, because the hypotenuse is always the side opposite of the right angle. Now, why do we bother with this terminology? Because back at the beginning, we didn't just say these were right triangles. We said these were similar right triangles. And what we've just established, because we know angle B is congruent to angle E, then this opposite leg, AC, is actually a corresponding side to DF. So the opposite leg of congruent angles are corresponding sides. So that means that the adjacent leg, which is in this case to angle B, line segment BC corresponds to line segment EF. Now, the diagram definitely kind of shows how that is, but defining these certain segments based on a certain angle, we can actually define which sides are corresponding, which helps us when knowing that those sides are supposed to be proportional. And we are diving into a lesson that talks about ratios. So it's important before we go any further to make sure that we have defined what it looks like according to an angle, what an opposite leg looks like, an adjacent leg, and of course the hypotenuse, because we are dealing with right triangles. Now, with all that information, let's dive into our lesson. So let's take a look at our learning targets for lesson 22-2. We are going to understand, hopefully, the definitions of sine, cosine, and tangent ratios. There's that word again. We're going to see it quite a bit. Understand the definitions of sine, cosine, and tangent ratios. Then we are going to calculate the trigonometric ratios in a right triangle. The trigonometric ratios. And remember, a ratio really is just a comparison of two numbers. And we're probably going to have some very specific numbers that we compare. And oftentimes in math, the way we write ratios, we could write it A to B. We could actually write it out A to B. Or one of the most common ways, and you're going to see here in these lessons, is we write ratios as fractions. Because a fraction really is a comparison of numbers. It's also division, but it's also a comparison of numbers. In fact, the fraction 2/4, we would say 2 is what of 4? What's the relationship there? Well, yes, you could argue it's 2 less, but really, in this sense, it's half of 4. 2 is half of 4. That's why, in fact, 2/4 reduces to 1/2. So that's all a ratio is. It's a comparison of numbers. And we're gonna pick out some very specific comparisons of numbers in this lesson. So we're going to understand definitions of sine, cosine, tangent, calculate those ratios in a right triangle, and then describe the relationship between the sine and cosine of complementary angles. Notice that we use that information at the beginning to talk about or recall what does it mean for two angles to be complementary. And it's two angles that sum to equal 90 degrees. So now that we have our learning targets established, if you would go ahead and draw a line at the bottom of this page. We're going to go and just chunk this table together, item 1, I believe. So read the text, look at the information here, and complete the table before playing through. Okay, hopefully you took a second to actually fill out the table here. And I highlighted some pretty important text for us before we just run through this lesson. Number 1, it said one group of similar triangles. Recall that similar triangles have corresponding angles that are congruent and corresponding sides that are proportional, which means their ratios are equal. And notice what you're doing here. You are determining the ratios and then writing those ratios in lowest terms. So some of you might have actually been surprised when you saw that in the table, these fractions, aka ratios, because they are comparing two specific sides of our triangle, you were probably surprised that these ratios were equal. But that's what it means to be proportional, to have ratios that are equal. So just to break down the table for you. So for grid A, for this triangle, and notice they labeled this angle actually A, and they did that for grid C, they labeled this angle C, and for grid E, they labeled this angle E. And so the L equals 8 actually refers to the longer leg in this diagram, which would be this leg here. And so I actually went ahead and labeled that it was 8 units. The S stands for shorter leg. So in this triangle, this would have been the shorter leg down here, and I labeled it 6. And then they also told us that H, the hypotenuse, is 10. So this is a 6, 8, 10 right triangle. Likewise on grid C, this is a 3, 4, 5 right triangle, the most common Pythagorean triple there is. And then in this triangle, this is a 9, 12, 15. And so on number 1, the table, you were tasked with comparing certain measurements, right? That's what a ratio is. It's a comparison of measurements. So in this first column, you were tasked with comparing the length of the opposite leg of an indicated angle, and the first one would be angle A, compared to the length of the hypotenuse. So for angle A, looking at angle A, the leg opposite of angle A is this leg here, which is 8 units. And so we put 8 in the numerator. Then they asked us to compare it to the length of the hypotenuse, which again, the hypotenuse, which is 10, is always opposite of the right angle. Regardless of what our indicated angle is in this table, the hypotenuse is always opposite of the right angle. So we wrote 8 over 10, which of course can be reduced to 4/5 because we can divide 8 and 10 both by 2. So we repeated that here for the length of what's known as the adjacent leg. Remember, if opposite of angle A is this leg, then adjacent to it is this leg. And so we compared the adjacent leg 6 to the hypotenuse 10. And of course, we reduced that to 3/5. And then last, we took the length of the opposite leg, which we've already established is 8, and compared it to the length of the adjacent leg, which is 6. And then we noticed as we started doing that for each angle, that these ratios started to be equivalent. And again, the main reason they are equivalent is because they're similar triangles. And similar triangles have corresponding sides that are proportional. Now that we've established that corresponding sides really are proportional in these similar triangles, let's now take a focus a little bit more intently on the angles. Let's look at item 2. In fact, if you would, go ahead and draw a line below item 4. We're going to chunk 2 through 4 together, but I'm actually going to explain 2 for you in case you don't have a protractor handy. So it says for each of the triangles of item 1, use your protractor to find the measure of the larger acute angle, which they're telling us angle A, angle C, and angle E in the diagrams are the larger of these 2 acute angles. So angle A is the larger of these 2, angle C is the larger of these 2, and of course angle E is the larger of these 2. So if you don't have a protractor handy, I'll provide those measures for you. Now we should know that angle A, angle C, and angle E are going to be congruent to each other because we are dealing with similar triangles, and similar triangles have corresponding angles that are congruent. So if you found the measure of angle A, which was 53 degrees, you'll know that angle C and angle E also have to be 53 degrees because we're dealing with similar triangles. Now that you have that information for item 2, complete 2 through 4 before playing through the video. Okay, so items 3 and 4 are really trying to broaden our mind. We had a couple examples and we started to notice that their ratios were all equal, specific ratios, of course, of corresponding sides. And so now on item 3, they're trying to get you to imagine if in another right triangle, the measure of a larger acute angle was the same as the measure of angle ACE, angle A, angle C, and angle E, what would you expect the following ratios to be? So imagine another right triangle that also had the same measure of this angle, 53 degrees. What would be the ratio of the opposite leg to the hypotenuse? And why do you see that they're all equal? Let's go back what it really means for triangles to be similar. So if I had another right triangle and the measure of one of the angles was the same as A, C, and E, and notice this is that 3, 4, 5, imagine that I took this right triangle from this angle here and just dilated it. Just dilated both sides proportionally. Still would have that 53 degree angle because, again, dilations don't change angle measures, so we would still have similar triangles. And the opposite side, let me get another color. The opposite leg, in fact, the opposite leg to that 53 degree angle from the small triangle would be proportional to the opposite leg of the larger triangle because it's still opposite of that 53 degree angle. So item 4 will help explain why these ratios are equal. If another right triangle had an acute angle that equaled 53 degrees, for example, this larger one here, then the triangles would be similar by angle. You could have also said, well, if you know this angle is 53 degrees, you know this is 37 because they have to be complementary. And therefore, this angle is also 37 degrees. And you could have said that these two angles, those two pair of angles could prove similarity, but we already know it's a right triangle. So I didn't even mention the 37 degrees here because if we know one angle is 53 degrees, they are right triangles, there's a 90 degree angle, then the triangles will be similar by angle. Therefore, if they are similar triangles, their corresponding sides would be proportional, aka their ratios are equal. So regardless of how big or how small these triangles we could create, as long as one of the angles is 53 degrees, then the ratio of the opposite leg to the hypotenuse is going to be the same for all of the similar triangles. And the ratio of the adjacent leg to the hypotenuse, again, will be similar for all the triangles. And the ratio of the opposite leg to the adjacent leg will be similar for all the triangles if the triangles are, in fact, similar. Now, if you recall from our previous lessons about similar triangles, there's tons of different ways to write proportions, or in fact, write a ratio more specifically. So if you notice, they kept referring to these specific ratios: the opposite leg over the hypotenuse, the adjacent leg over the hypotenuse, the opposite leg over the adjacent leg. These specific ratios, these specific comparisons actually set the stage for the 3 trigonometric ratios we saw in our learning targets. The ratio of the lengths of 2 sides of a right triangle is known as a trigonometric ratio. Say that enough, it'll make you sound smart. And the 3 basic trigonometric ratios are sine, cosine, and tangent. And they're often abbreviated to look like sin, cos, and tan, but we will still say sine, cosine, and tangent. Now let's chunk item 5 and 6 together, but I'm actually going to work item 5 with you to show you how to use a scientific or graphing calculator. There's 2 options here I'm going to show you. If you actually have a graphing calculator, I'm going to show it to you with a desktop calculator I have here. So they're asking us to, let me make sure it's turning on. There we go. They ask us to use a scientific or graphing calculator to evaluate each of the following to the nearest tenth. The nearest tenth. So they're asking us to find the sine of 53 degrees, the cosine of 53 degrees, and the tangent of 53 degrees. And it says make sure you're in degree mode. So on your graphing calculator, make sure you are, if you hit mode, make sure degree is highlighted. And then to access sine of 53 degrees, we're just going to hit the sine key and then type in 53. It's always a good idea to close those parentheses, and they ask us to evaluate it. And notice it's a decimal, 0.79, and they ask us around to the nearest tenth. So we'll say that the sine of 53 degrees is 0.8. Now let's repeat that process for the cosine of 53 degrees. So we're going to do the same thing, hit the cosine button, type in 53, close parentheses, and we find that the cosine of 53 degrees is 0.6. And we're going to figure out where all this information is leading to in item 6. So just hang with me. We're just finding the decimal approximation of these three ratios, the sine of 53, cosine of 53, and the tangent of 53. So the tangent of 53 is 1.32. So we'll just say 1.3. Now, if you don't have a graphing calculator like that, I'll show you how to use it on something called Desmos, which is an online graphing calculator. So if you go to desmos.com and then click on the graphing calculator, over here, this is where we're going to input our sine, cosine, and tangent of 53 degrees. Before we do that, if you click on the little wrench and make sure you are in degree mode. So just like we changed that for the graphing calculator, make sure you change that here. Otherwise, you're going to get a very different answer. So to use Desmos, we are going to simply type in sine, which we're not going to type in the E, just the SIN, of 53. And notice when we type in sine of 53, it gives us that same decimal approximation. I'm going to go and show you how to do cosine as well. Cosine of 53, there's that same decimal approximation. And last but not least, tangent, which we're just going to type in tan for tangent of 53, which again is 1.32. So now what I want you to do is complete item 6 before playing through the video. So hopefully you noticed something pretty peculiar happening here. We discovered that the sine of 53 degrees, sorry about that. But anyway, we're probably still trying to wrap our minds around what exactly sine of 53 degrees really means. And all we know of it is it's a decimal, roughly 0.8, and cosine of 53 is 0.6. But we saw this 53 degrees somewhere previously in our lesson. In fact, it was that measure of those acute angles. And then in item 6, they ask us to write those ratios from item 1 as decimals. And we saw in the first column, the opposite leg of the hypotenuse, that fraction was 4/5, and that as a decimal is 0.8. And then B, the adjacent leg over the hypotenuse, was 3/5, and that decimal is 0.6. And then last, the length of the opposite leg over the adjacent leg in the third column was 4/3, which was 1.3. And we noticed something going on here between these two items, that the sine of 53 degrees, 0.8, is equal to the ratio we wrote opposite leg over hypotenuse. So the first question I have is, what was the opposite leg of? Well, go back to item 1. This opposite leg was the opposite leg of that 53 degree angle, 8/10, or in this case, 4/5. The length of 4, that side was actually the opposite leg of the 53 degree angle. So with that in mind, sine of 53 degrees is the same as the opposite leg over the hypotenuse of a 53 degree angle. This is introducing us to the trigonometric ratio. So let's look at item 7. It says, compare your answers to items 5 and 6, then describe each of the ratios below in terms of sine, cosine, and tangent. Assume that the ratios represent sides of a right triangle in relation to an acute angle x. So for example, or to explain this really, we know that the acute angle in our diagram is 53 degrees. So we're saying that the ratio that compares the opposite leg of that 53 degree angle to the hypotenuse of that 53 degree angle is the same as the sine of 53. And likewise, we're saying that the ratio that compares the adjacent leg to that 53 degree angle to the hypotenuse of that 53 degree angle is the same as the cosine of 53. And last, the opposite leg of the 53-degree angle compared to the adjacent leg of the 53-degree angle is the same as the tangent of 53. These are known as our sine, cosine, and tangent ratios. So when we compare the length of the opposite leg to the length of a hypotenuse in any right triangle, this is known as the sine ratio. And so we could say the sine of x, because we're talking about, in this case, just some obscure angle x. So the sine of a 53-degree angle was the comparison of the opposite leg to the hypotenuse. And notice those ratios are all going to be equal because we're dealing with similar triangles. So the adjacent leg to the hypotenuse, when we compare the length of the adjacent leg of an acute angle to the hypotenuse of that acute angle, it's known as the cosine of that angle. And last, when we compare the length of the opposite leg of that angle to the length of the adjacent leg of that angle, it's called the tangent. So notice we're writing ratios of similar triangles based on a particular angle. So now that we've defined the sine, cosine, and tangent ratios, let's take a little opportunity to practice those ratios, writing them in simplest form. So we're going to go and chunk item 8A through D together. So go and draw a line at the bottom and complete A through D before playing through the video. Okay, so hopefully you took the opportunity, and I know it's a new idea and it's probably a little bit heavy, but don't overcomplicate it. We are asked to write ratios, which we're typically writing those ratios in fraction form. We know another way to write a fraction is a decimal, so you could write 8/17 eventually as a decimal. And so we are tasked for the sine of A. What that really means is compare the opposite leg of angle A, compare it to the hypotenuse. So in reference to angle A, the opposite leg is side BC, which is 8. And the hypotenuse of that triangle, regardless of which angle we're looking at, is line segment AC, which is 17. So the sine of A, the opposite leg of A to the hypotenuse of A, is 8/17. Now the cosine of A, as we just defined in item 7, is the adjacent leg of angle A. So the adjacent leg of angle A is actually AB, which is 15, and compare it to the hypotenuse, which, again, regardless of which angle we're looking at, is 17. And then last, the tangent of A, we compare the opposite side, which we already established was 8, the line segment BC, compared to the adjacent side, which is, again, line segment AB, which is 15. And then we noticed something peculiar here, and the whole idea was to write the ratios looking at angle A as the indicated angle, and then write those ratios looking at angle C. So the sine of C clearly should be different than the sine of A. The sine of C is the opposite leg of C compared to the hypotenuse of C. So the opposite leg of angle C is actually this leg here, which is line segment AB, which is 15. And again, the hypotenuse, regardless now that we're looking at angle C, the hypotenuse is still 17. And the cosine of C is the adjacent leg, which would now be BC, which is 8 units over 17. And last, the tangent of C, the opposite over the adjacent. So opposite of angle C is 15, adjacent is 8. And they wanted you to draw a pretty heavy conclusion here because we know we should notice some correlation between these different ratios. But before we go too far, let's look at B. How are the two acute angles of triangle ABC related? And you might be wondering, scratching your head, how do I know they're complementary? We don't know any angle measures. Well, again, the three angles of any triangle has to add equal 180 degrees. And if this right angle already takes up 90 degrees of that 180, these other two angles have to sum to equal 90 degrees on their own. And that is the definition of complementary. So in item C, we want to draw the conclusion there's some particular relationship between the sine and cosine of complementary angles. They are in fact equal. If you notice here, the sine of angle A is actually congruent or equal to the cosine of C. And likewise, the sine of C is congruent or equal to the cosine of A. And the last thing I want to point out, and the book didn't mention, is actually the tangent of complementary angles are reciprocals. Reciprocal means to flip. And so the tangent of A was 8 over 15, and the tangent of C was 15 over 8. But regardless, the sine and cosine of complementary angles are actually equal. So item D, they want you to apply that. If you know the sine of 68 degrees is approximately 0.93, what other trigonometric ratio do you know? Well, we just established here that the sine and cosine of complementary angles are equal. Well, the complementary angle to 68 degrees is 22 degrees because 68 plus 22 is 90. So we also know, even without a calculator or without a diagram, that the cosine of 22 degrees is also approximately 0.93. Now, because this lesson can be rather heavy, although we've kind of reduced it to some pretty basic ideas, that sine, cosine, and tangent are just really ratios comparing certain sides. Let's take the opportunity to work the check your understanding. I'll go ahead and draw a line. So let's chunk 9, 10, 11. Try those first before playing through. I love question 9. So hopefully you took the opportunity to go back and study our 30, 60, 90 triangle from lesson 21. And so it said, explain how to write the sine of 30 degrees as a ratio in simplest form without knowing the length of any side of the triangle. So what we're establishing here is any right triangle that has angle measures 30, 60, 90 is going to have ratios that are equal because their sides are proportional. And we established a special relationship back in our 30, 60, 90. For example, we learned that whatever the length of the shortest leg was, and again, the shortest leg will be opposite of the 30 degree angle, whatever the length of the shortest leg was, the length of the hypotenuse was always twice that length. So notice here, I said that the shortest leg was x, and the hypotenuse is 2x. And we also established that if we know the length of the shortest leg, we can multiply it by the square root of 3 to get the longer leg. And we wrote something very similar to this, describing the hypotenuse. The hypotenuse is equal to twice the length of the shorter leg. So with that in mind, the sine of 30 degrees, which is the opposite side, which would be our shorter leg, compared to the hypotenuse of that type of triangle, the sine of 30 is some measurement x over twice that. Well, you can simplify these two x's. They would actually cross out. And you might be asking yourself, well, what's left over? Well, what's really happening here when we say cancel, x divided by x becomes 1. So the sine of 30, x over 2x, the sine of 30 is 1/2. Because whatever the relationship of the shortest leg is in that triangle, the hypotenuse is always twice that big. Or another way to look at it is the length of the shortest leg is always 1/2 of the hypotenuse. That's what a fraction is. It's a comparison of two numbers. More specifically, this comparison is the opposite side of an angle compared to the hypotenuse of that angle. Now, item 10, interesting question. Suppose you know that triangle RST is a right triangle with right angle at angle R. So our two acute angles are going to be S and T, which we've already established. Those two angles have to be complementary angles. And what we just saw in item 8 is that trig ratios of complementary angles can be equal. So the cosine of S, which is 0.67, is going to be equal to the sine of the complementary angle. So if the cosine of S is 0.67, then the sine of its complementary angle, which would have to be t because we established angle R is the right angle, then the sine of t also has to be 0.67 because the sine and cosine of complementary angles are equivalent. So just expounding on what we did on item 8. And then number 11, I really like this question because it goes back and it applies what you learned in lesson 20 using the Pythagorean theorem. It says, given the sine of b is 5 over 13, draw a right triangle ABC with right angle C and label the side length. So initially, you don't know that this side is 12, but I drew a right triangle ABC, labeled C as the right angle. And the reason I knew this side had to be 5 was because I labeled this angle B, opposite of that has to be 5, and the hypotenuse has to be 13. That's what the sine of B tells me. The opposite leg of angle B has to be 5 units, and the opposite side, the hypotenuse of B has to be 13. So with B being the indicated angle, opposite of that is 5, and the hypotenuse is 13. Which the first thing they ask us to do is to find the missing side. Well, it is a right triangle. Don't forget that if you have a right triangle, you can find the missing side using the Pythagorean theorem. So recall that we are finding the length of a leg, so that could be A or B in the Pythagorean theorem. Make sure that 13 is the hypotenuse that you plugged it in for variable C. So we did a squared plus 5 squared equals 13 squared. Got down to a squared equals 144. Took the square root of both sides, and lucky for us, 144 is a perfect square of 12. So then I went back and labeled that this missing side is 12 units. Because on a B, they want us to write the cosine of B. So the cosine of B is the ratio comparing the adjacent side of B, which the adjacent side of B would be this side BC, which is 12, comparing it to the hypotenuse, which we've already established is 13. So the cosine of B, 12 over 13. Last and certainly not least, the tangent of B is the opposite side of B, which we've already established is 5 back here in the sine of B, 5 over the adjacent side of B, which we just established is 12. So the tangent of B, oh, I see I have an error. It's 5 over 12, not 5 over 13. So that is the end of lesson 22-2. As always, complete the practice and go back and reevaluate your learning targets. Hopefully, we're feeling somewhat comfortable with these new trig ratios. Thank y'all for watching.